Now we are going to talk about this parity criteria to exactly identify what is a topological insulator. As I said, band inversion is a very intuitive picture, but sometimes actually the band inversion is not always that clear, and we need some accurate numerical method. And the consequence of the band inversion is the surface states. As you remember, the surface states is a Dirac coin. Actually, the Dirac point, the robustness of Dirac point is protected by time-Russell symmetry. Therefore, time-Russell symmetry defines the topological invariant. And for time-Russell symmetry, well, in the momentum space, actually not every point has this symmetry. In the 2D and 3D momentum space, there are only limited number of time-Russell invariant K points. For example, the gamma point and the boundary of the Brillouin zone. And by investigate the time-Russell symmetry eigenvalue to the block wave function, and we can define the topological invariant. Actually, by count all these delta R numbers and plus minus 1, we will get is a topological insulator or regular insulator. However, in reality, it's difficult to calculate this time-Russell symmetry eigenvalue. But if at the same time the system has additional symmetry, for example, the inversion symmetry, actually this problem becomes much easier. Here, this delta R becomes exactly the parity eigenvalue. Let's look at an example of a three-dimensional insulator. These all the 8 time-Russell invariant momentum space. Actually, here there are 3 x points and 3 m points. Let's think about the most simple insulator is atomic insulator. Then, if it's atomic, there's no dispersion. Then the valence band and conduction band just flat, right? Now let's suppose we only have one single atom. We have a p orbital for the valence band, s orbital for the conduction band. We know the parity eigenvalue for p orbital is always minus, s is the plus. And in this case, let's follow this formula. We multiply all these parity for the occupied bands. These bands below the frame energy, actually we have 8 minus. Then whatever, 8 minus, the product is plus. We get a trivial topological invariant, right? We get mu 0, 0. And then now let's put this atom closer. We start to have some dispersion. We have an insulator with the band dispersion. However, the valence band is still p orbital, the conduction band is still s. Therefore, follow this criteria, we get another plus 1, all this parity eigenvalue. Then as long as we have a band inversion, the s and the p start to invert. At the invert, we get a parity switch. With this parity switch, we get a non-trivial topological invariant. Then this is a topological insulator. Here, this table lists all the parity eigenvalues. With it, we can simply get this topological invariant mu 0, 0, or 1. Then let's see a general. This not only applies to 3D, actually to 2D. Let's look at 2D insulator. We have only 4 time-Russell invariant momentum. Here, if we have a minus at gamma, therefore these 3 product we get a minus 1. In this case, the topological invariant is 1, is a 2D Ti. If we stack this 2D layer to 3D, we get a 3D material. Suppose the Kz dispersion is weak. If it's weak, the gamma plane and the Z plane will be identical in the wave function symmetry. Therefore here, this is the parity, the Z is minus again. You see the total parity product, we see because there are 2 minus, total parity product is 0. This is like follow that criteria, it's not a topological insulator, but we know because the 2D plane has a boundary states, it has topology, it has edge states on the boundary. If we stack these 2D layers, this surface, the side surface, will be still metallic. It comes from these 2D topological states. But the top surface is insulating, right? In this case, it still has some information of topology. In this case, we call this system as a weak topological insulator. And we invent this new topological invariant, this mu1, mu2, mu3. How mu1, mu2, mu3 are determined? Actually, for example, the mu3 is determined by the z plane. The mu1 is determined by the x plane. The mu2 is by the y plane. And very easily, we can get mu1, mu2 are 0. And if the Kz dispersion are slightly different, for example, here the gamma becomes plus, well, immediately we know the total product is -1. Therefore, we get a strong index mu0. And we also have this weak index, mu1, mu2, mu3 is 0, 0, 1. This is the case of a strong topological insulator. But what's the difference between a strong one and a weak one? The weak one, we said the side surface is metallic. It comes from the edge states. The top surface is insulating. However, for a strong one, every surface are metallic. It has a metallic skin. This is the early example we learned from the band inversion. And one last note I want to mark is, here we talk the language, like in the band structure, we talk language of p orbital, s orbital. And this, we know the p orbital has minus parity, but this applies only for if we have only single atom in the unit cell. If we have many atoms, this can be different. S orbital can give you minus parity. For example, if we have an antibonding state, here the red represents the inversion center between two atoms. The antibonding state is minus parity, the bonding state is plus in parity. Then that is opposite for the p orbital, for the px and the pz, they are different. Therefore, for the parity we talk about is the parity of the block wave function, not limited to the atomic composition. Then with this parity method, we can exactly calculate the topological invariant. We know it's a topological insulator, 2D, 3D, weak one, strong one. However, there's a precondition, remember. We request that the system has inversion symmetry. If there's inversion symmetry is broken, how do we do? That is the next example, next method we'll talk about is the Wilson loop method. Then see you in next lecture.